Morning. Clearly there's an awful lot of sleepy people. I wonder why. So very good for you to come and join me. If you remember yesterday, we started to talk about integration. And the example that we looked at was the computation of multiple integrals numerically for this computer graphics problem. And the argument that was made was that a probabilistic perspective on the numerical approach to integration would make sense in the way that I had argued from a perspective of looking at the problem not simply from a numerical perspective, but from a statistical or probabilistic perspective. And what we saw yesterday was that if we were to define a Gaussian measure, a Gaussian process measure on the function that we were going to integrate with respect to some probability distribution or weighting function, then because the integral operator is linear, then the push forward of that Gaussian measure on the integrand yielded a Gaussian measure on the integral itself. And what we saw was that the mean value for the estimated integral and the corresponding variance of it looked like this here. And these are the standard results from Gaussian process conditioning on data. In this case, the data was the evaluations of the function f. And the main point to note is that the integral operator, pi, appears in the mean function and in the variance function here, where the representer of the RKHS is defined by the integral of the covariance function. And it's absolutely clear that to make this a practical method that you could implement, then being able to analytically obtain the value of the integral of the covariance function is absolutely essential. And so what that suggests is that there is a small, and indeed a very small, class of problems where we could actually employ this particular scheme. But in the class of problems that we can employ it, then what is very nice is that we can prove that the rate of convergence of our estimate will go as order of 1 over n to the alpha over d, where d is the dimensionality of the space, and alpha is the smoothness of the function. And if we assume that d is 1, so if we are just treating a one-dimensional integral, then what we see is that the smoothness of the function that we want to integrate is a function of the theoretical achievable rate of convergence. So the smoother the function, the faster the rate of convergence. So this is very nice. Can anyone see a problem that might emerge here? What if the dimensionality of the problem was 100? What does that suggest? Exactly. So what in fact happens is that as the dimensionality of the space increases, then this rate of convergence is just going to, it's basically going to decrease down to the standard Monte Carlo rate. And so what you have is a curse of dimensionality inherent here, and in fact inherent in any data analysis method. So that's one thing to notice, right? That although the estimator now exploits the fact that we are taking into account the smoothness of the functions that reside in the space we are operating in, at the end of the day, if we are still going to be working in a high-dimensional space, then we may well lose any benefit that we accrue. So that's something just to bear in mind. But in any case, this is a nice result, an interesting one. And we looked at the sort of performance that we could achieve. And in fact, for the little example I gave you, we can get rates of convergence as 1 over n to the 3 over 4, which beats Monte Carlo, and the results looked quite promising. So that's very nice. Now, of course, the main issue here is that we have to be able to compute this integral of the covariance function. And if we can't do that, then really this is an impractical approach. So how can we extend this to cases where we have density, or we have distributions that we want to integrate with respect to, and they have densities defined with respect to some dominating measure, where it is intractable, where we may not know what the normalizing constant happens to be, and therefore we cannot compute the representer of our kernel. Well, there is some work that myself and some of my team did, and was published in the Journal of the Royal Statistical Society, Series B, which is the main methodological journal of the Royal Statistical Society. And what we did is we developed a probabilistic numerical scheme which we called control functionals. And this is a generalization of what one of the speakers presented for variance reduction, which was called control variates. And we have developed this approach called control functionals. And so what I want to do is present to you in a very intuitive way the underlying concepts of control functionals for Monte Carlo integration. And then once we've done that, if you're still awake, or we still have time, then I'm going to go through I'm going to go through it again, but in a more formal way and in a more abstract way. So, just to remind you, again, is that the problem that we are looking at is integration, and in particular, integration with respect to some dominating measure or density, or measure that has a density, pi. Okay, so we're looking to obtain estimates of this type of integral. So pi is some density of the associated random variable x, and it's defined on a probability space, so defined by the probability triple, and it takes on values x in the measurable space, so the usual definition. And in this case, we can just assume that the reference measure is Lebesgue measure if x, calligraphic x, is defined in RD, or some kind of Hausdorff measure if we are working on a manifold. Now, again, this can be a really very non-trivial problem. So those of you that are working on large scientific problems, so to do with weather forecasting, with atmospheric science, some very large complex engineering or physics problems, then computing expectations like this can be extremely challenging. And it can be extremely challenging because, as I mentioned yesterday, the integrand, the function itself, can be very expensive to compute. So f could be the output of some simulation of the global weather system, for example, or a simulation of an oil field's characteristics over a certain period of time. The other one is that the density that we want to integrate with respect to is intractable. Right? So we can't simulate easily from pi to obtain our estimate. And in the sort of applications that we see for Bayesian statistics and machine learning, we have both of these problems occurring. And so the probabilistic numerics approach is one way of trying to resolve this problem. Just to illustrate, imagine that we are trying to solve a non-trivial inverse problem, and our data is generated by some observations. So in this case, observations of a global weather system, so perhaps satellite images, and then localized traces of local weather conditions. So that's our data, and then our model would be the output of some large-scale simulator. Okay? So the likelihood of our data, represented by the kind of lightly colored world, right, conditioned on our model, is going to be difficult to compute because we have to run a model of the global weather system. And then furthermore, if there is some quantity of interest that we want to derive from our computer simulation, so that in itself may be very complex. And therefore, if our integrand is some function of the solution of a very complex model, then obtaining expectations of this function would have to be estimated using a very small number of samples. One, because it may be difficult to obtain the data, and two, running this simulator may be extremely expensive. And of course, the problem that we face then is that our estimates, using a small number of points, where n is only 10 in this case, the level of variance could be so high as to render any inferences that we would be able to make based on this approximated expectation pretty much useless. So we really are motivated by the need to improve the rate of convergence. Now, there are lots of approaches that have appeared in the literature to improve upon the base level Monte Carlo method. And the Monte Carlo method is very nice because it is an unbiased estimate. But if the density pi is intractable, then we can't use the Monte Carlo method, and its rate of convergence is 1 over root n. So we don't get any better than that. And it's not something that we can apply in any kind of post hoc way. And then, of course, there is Markov chain Monte Carlo, which is not unbiased. It is a biased estimator, but it works in the cases where straightforward Monte Carlo would not work, when pi is intractable. But again, the rate of convergence is still no greater than 1 over root n. And then if we kind of go down the list, there are a whole host of things. If we look at control variates, we see that control variates using just Monte Carlo can be unbiased and can be applied in a post hoc way. So in other words, we don't need to write specialized codes to implement this. But I suppose the approaches that we're interested in are those that can achieve a greater or a faster rate of convergence than 1 over root n. And these are the class of problems based in quasi-Monte Carlo. And then, of course, there is one approach based on Riemannian sums, but that is only useful for one-dimensional problems. And then, of course, there is the Bayesian quadrature, which I presented to you. The control functionals approach, which I'm going to describe to you, does provide an unbiased estimator. It can be run when pi is intractable. It does provide a provably greater rate of convergence than 1 over root n, and it's very simple to implement. So we don't need to rewrite any particular computer codes. So what is this control functionals? Well, let's just remind ourselves what control variates are. So let's say that we have a statistic derived from a sample of random variables x, so our statistic is u, and that statistic is such that its expected value is 0. And one statistic that we could use is the score function. The score function is the derivative of the log of the data probability, or the likelihood. Okay? And schoolboy statistics will tell you that the expectation of the score function is equal to 0. So we could use the score function as what would be called a control variate. And what is that? Well, we would devise an estimator for our integral of f with respect to pi in the following way. We could take our standard Monte Carlo estimate, 1 over n, of the sum of the evaluation of the function at each of the points xi, and to that we would add a weighted combination of the score function, or this statistic u of xi, right, for each of the sample points. Now, if you take the expected value of mu hat control variate, then what you'll see is that because this component is 0 and the Monte Carlo estimate is unbiased, then this estimator is going to be unbiased. So that's good. So we haven't broken anything by adding this sum of the the control statistics to the Monte Carlo estimate. So that's good. But A, the vector A, well, that's just been arbitrarily defined. And it turns out that if we look at the variance associated with our Monte Carlo estimator and the variance of our control variate estimator, then the ratio is such that it's equal to 1 minus the correlation function between the integrand and this statistic here. Now, it turns out that this will always be, if the correlation between the integrand and the control statistic is perfect, so in other words, the correlation is 1, then the variance of our estimator is 0. So we have a way of potentially improving the variance of our estimator. So this looks good. And it turns out that in a very simple case, so if we wanted to just take the average of some random variable x, so our function f is just linear, it's just x, and the probability distribution is Gaussian, then it doesn't take much schoolboy algebra to show that the variance of the estimator will in fact be 0. The thing is, though, that although the variance of the estimator can be reduced, the rate of convergence will still remain as 1 over root n. So on the one hand, we get a better estimator with a lower variance, but we don't do anything, we don't achieve anything in terms of improving the rate of convergence of that estimator. So, can we do any better? Well, let's see. Let's just remember that our control variate estimator is just equal to the sum of the integrand computed at a point xi plus this projection of our set of control statistics onto some vector A, which we can optimally choose. And what we'll do is we'll say that we're going to replace our function f with the function f tilde, where f tilde is basically just this here. So f tilde is just f of xi plus A transpose u of xi. This isn't strong enough. Now, what does this mean exactly? Well, it means that in terms of control variates, what we're doing is we're replacing the function f by the function f tilde so that the expected value of f tilde is just the same as the expected value of f, and the variance of f tilde is going to be smaller than the variance of f. Okay, so we're looking for a surrogate function whose variance is lower than the actual function we're interested in the first place. So what we can do is we can take quite a general approach here, and we can say the following. We could write this here So f tilde is equal to f of x plus, well, A transpose u of x is just some other function, right? And what we can do is we can say, well, let's write this more generally, and we're going to call f tilde, it's now going to be equal to f, and then it's going to have this term here. So this is us now generalizing the A transpose u term. So we're going to have an f hat, and then the expected value of f hat. Okay? And we're going to say that f hat is an approximation, and it's a tractable approximation, so it's a computable approximation to the function that we're interested in. And again, if we take the expectation of f tilde, we can see that this term on the right will cancel out, and so any estimator based on f tilde is going to be unbiased. And what about the variance? If anyone has any questions or wants a point of clarification, just shout or stick your hand up. So what about the variance? Well, the variance, it turns out then that we want the variance of the sum of the evaluations of f tilde. And that's just going to be equal to the usual. It's going to be equal to 1 over n times the variance of the difference between f and f hat. Now that's quite interesting. The variance of the control functional estimator. So remember, all that we've done is we've taken the control variate and we've generalized it to some function which is an approximation to the integral or the integrand that we're interested in. So we've now changed from thinking about variates, finite dimensional variates, to actual functions themselves with f hat. Now look at this. The variance is the variance of the integrand minus f hat, the approximation of the function. So what this suggests is that if I can make the error between my function and my approximation of it as small as possible, then the variance of my estimator will become as small as possible. So the key idea that we had is that if we can make the approximation f hat as good as possible so that f hat is almost equal to f, and that it gets better consistently with n, then the variance of the error, f of x minus f hat of x, will tend to 0 as n tends to infinity. So this is the principle that we're going to work on, and we're basically calling this control functionals, and we call it control functionals because we're no longer looking for a set of control variables. We're looking for a functional that will approximate the integrand that we're interested in. So how do we do that? Well, we want to consider two things. So first of all, f might be unknown. So f might be the output of some big simulator. So as I said, a global weather or atmospheric simulator. So we can't write f down as some function. And pi is going to be intractable. So it's only going to be defined up until some normalizing constant. So what we need to do is we need to be able to obtain our approximation f hat in some way that is automated. So we're going to consider a class of functions that are induced by an operator. And that operator is called the Stein operator. And if we have time, perhaps this afternoon, I will talk about the Stein operator. But for the time being, let's just assume that there is some operator named after Mr. Stein, and it takes the form of this here. Right? So we're going to say that f hat defined by the Stein operator is equal to this thing here. So let's just unpack this. So C is just some constant. Grad with respect to x, and then the divergence of some function phi of x, right? So this is just the divergence. So phi of x is the class of functions that we're going to choose to approximate f hat. And then we have this term here, which is the dot product of the function and u of x, where u is the score function with respect, or defined with respect to pi of x, which is the density that we want to integrate with respect to. So that's the class of functions that we are going to be thinking about in estimating or approximating f. The class of functions is going to be defined by a constant plus this function here, which operates on some basis set, and the basis set is combined with the score function of the density that appears in the integral. Now, just a few little things to note is that just some standard results tell us that, or I should say the x, the domain is bounded, and in which case the product of pi of x, phi of x, for points x that are on the boundary is equal to 0. And because of that, it means that the expectation of f hat is just going to be equal to this constant c. So that means then that we now know what this constant should be. It should be the expectation It's his mother telling him to get up out of bed. So what this is telling us is that the expected value of all of this here, right, is equal to 0, and therefore the expectation of f hat is equal to c. Okay? So we've got a tractable approximation. So we want to now specify c and phi, and of course the way that we want to do it is so that f hat will minimize the variance of f and f hat, the difference between the two. Okay, so this is going to be an optimization criterion. We want to minimize sigma squared phi with respect to c and phi. And then what this basically corresponds to is a functional regression problem. So we are going to say that the function that we're interested in is equal to some mean, and then this functional here, plus whatever the error happens to be. So we want to minimize the mean squared error between f and this here, which of course is just going to be, well, the mean squared error is just the expectation of epsilon squared, so sigma squared phi. So this is just functional regression. So how do we do this? Right, let's say that we obtain some samples x1 to xn from the distribution that has density pi. And we'll do two things. First thing is that we'll split the data into two sets, D0 and D1. Now you'll see why we do this just shortly. What we're going to do is we're going to use the subset of data, D0, to construct our approximation of f hat, our approximation of f, which is f hat. And the way that we're going to do that is estimate phi. Okay? So we take a subset of the data and we use it to solve the functional regression problem, and we get our estimate of, we get our approximation of f hat. And then the remaining data, D1, we use it to evaluate the average. Okay? So we've got f, or we've got evaluations of f, and we've got our evaluations of f hat. We sum these over all of the points in D1. We know what this is because we've approximated it. And that turns out to be our estimator. So there's two things we do. We approximate f using f hat, and then we estimate our integral of f with respect to pi using this approximation that we've just obtained. And if we use only the data, so let me start again. If we use data for our Monte Carlo estimate that was not used in obtaining our approximation f hat, then this estimator will be an unbiased estimator of the integral we're interested in. So, in fact, we could use any data. We don't need to use data from pi to approximate f. We could use all of our data in obtaining this numerical plug-in average, if we so chose. Okay, so this is all fairly simple. So what exactly is happening here? So let's just remind ourselves. Our estimate is equal to the weighted sum of f minus f hat, where f hat has been approximated using this expansion, or this functional regression here. So we're using this class of function for f hat. So how does this whole thing work? Well, here's an illustration. The green line shows the function that we want to integrate, and the blue dashed line is the density that we want to integrate the function f with respect to. Okay? So those are the two objects that appear in our integral. Now, what we do is we take a subset of points from the density, we call them D0, right? And we evaluate our function at each of those points. We then use those points to construct our functional approximation to f. And so here's our functional approximation. And the functional approximation will then give us the value of c, its expected value. And remember that in our approximation, in our estimate, we're using the sum of the difference between f and f hat. So there's f, there's our constructive f hat, and there's the difference between f hat and f. And what you can see is that the better f hat becomes, then the closer the green line becomes to a straight line at c, the value c. Okay, so we then take our data, our second set of data points from pi. We evaluate f minus f hat at each of those points, and then we just take the average. Now, what's actually quite interesting here is that what we're doing, so the better the estimate, the better the approximation that f hat is, then the smoother this is, and the smoother that is, then the greater the rate of convergence we obtain. And so the rate of convergence is actually higher than 1 over root n. And we'll get into exactly what that rate of convergence is just shortly. But does anyone have any questions about how we construct this estimator? So at the moment, all I've done is really just taken an algorithmic perspective of describing how we construct this estimator, and tried to give you an intuition as to why it would work. So in essence, what we're doing is we're replacing the original function with basically an error function, and the error function is the error between the original function that we're interested in, this one here, and its approximation. And so as the approximation gets better, then the function that we are effectively integrating with respect to is going to become potentially just a constant. So very smooth. Does anyone have any questions on that? Yes? Yes? Could you speak up? You need to be able to compute a value for f. So you need to return the value of f at a particular... Yes?
So if one just takes the average between this Schwarzschild function and the point of the true function, is it important that the true function is somewhat stationary, or what happens to the function that actually has changes its value by a large amount, or the domain needs to be a problem, or there are practical problems in this situation?
No, because what that means then is that the level of smoothness is quite low, or it may well indeed be non-stationary. I mean, clearly then that becomes a much more challenging function to integrate because of the high energy. The spectral content is quite complex in comparison to something that is smooth. So what we're trying to do here is take a function like yours, which may have a lot of energy in it and basically smooth it.
It's probably a stupid question, but the difference between the two, the f and m hat, you plotted with a line in color. Should be closer to zero than approximations?
Yes, but what we're doing is it's the function plus c. So we're shifting it to by c, that's all. There is never a stupid question. The stupid questions are the ones that don't get asked. Okay, so, well, if I just briefly show you some of the theory associated with this, I think there's a couple of things. So first of all, we really need the domain to be bounded. And in some cases, you might see that as quite limiting. But, well, in most applications, the domain typically is bounded. So I don't really see that as a limitation. But it's certainly a requirement for the theory to go through. The other one is, of course, is that we expect the density to be bounded away from zero on the domain. So in other words, the domain has full measure. Okay, so there's no points where there is zero measure. And the key thing here is that we assume that pi, the density, right, is a function, it's a continuous function which has got 2a plus 1 derivatives. Okay, so that tells us, so a is going to give us the level of smoothness. And k, so what I haven't told you is how we construct the functional regression estimator. And the way that we do it is using a Gaussian process. So therefore, there's going to be a covariance function. And the covariance function, again, as we heard in yesterday's lecture, the smoothness is going to be defined by, if we want a B level of smoothness, then the covariance for the function, then the covariance function would have to be 2B smooth.
Can you track, while doing this, can you track if you're converging, do you have bounds of convergence in practice?
Yes, you'll see these, yes. And in fact, you saw them in this previous example where, we don't rely on bounds. What we rely on is the actual variance itself. Oh, I'm in the wrong set of slides, that's why. Anyway, yes, the answer is yes, and I'll expand on that just shortly. So what else have we got? So it turns out that the error between the integral of interest and our estimator, so the squared error, goes at the rate of 1 over n, or so n to the minus 1 minus the minimum between, or so 2 over d, where d is the dimension of the domain, and the minimum between a and b. Or is that the maximum? Is that maximum or minimum? I think it's maximum. So what that's telling us is that the rate of convergence is going to be gated by the smoothness of the function, the integrand, or so it's minimum actually, I think. The smoothness of the function or the smoothness of the density. So whichever is the smallest. And so therefore your question about functions that have take big kind of jumps, these would not be very smooth, and therefore would be the gate as far as the rate of convergence is concerned. So this is nice because what this now does is it imposes additional mathematical structure. So the Monte Carlo rate of convergence really does not exploit any mathematical structure with regard to the class of functions of the integrand or the class of functions of the weighting function or the density that we're integrating with respect to. And what we've done here is we've taken that structure, the fact that the functions reside in some Hilbert space, and therefore, or Sobolev space, and therefore there is an inherent notion of the smoothness of the functions, and we've exploited that. And furthermore, the integral, or the density that we're integrating with respect to also has structure, and we are taking that into account as well. And taking both of these mathematical structures then leaves its imprint on what the achievable rate of convergence is going to be for this control functional estimator. So this is really quite a nice result, and it's a very practical result as well, as you'll see just in a moment. So how do we actually estimate this thing? Well, as I said, we use a Gaussian process, and the covariance function of that Gaussian process is constructed by, in essence, the operator that we use in defining our function, right? So this operator acting on the basis function phi, okay, is equal to the divergence of phi plus the inner product of phi and the score function. So we construct our covariance function based on this here, and so what that then means is that the Gaussian process, so the stochastic process that we're using to approximate our function, is now constructed, the covariance function is now constructed based by taking the mathematical structure of the function space and the space associated with the probability density. I won't go into the details of how we construct that, but it's fairly straightforward. And our estimator looks like this. So K0, the matrix K0, is going to be the square matrix of the covariance function evaluated at all of the points that we use to construct the approximation. And F0 is the evaluation of our desired integrand evaluated at all of the points that we're using to construct the approximation. So this term on the right is evaluated only on the points that are used to construct the approximation, and then the remaining points are used to obtain this plug-in average here. So F1 is the integrand evaluated at all of the points that have not been used to construct the approximation. F hat 1 is the evaluation of the approximation at those same points. So, I mean, that's basically the estimator. So again, the key point is that D1 enters only in this term on the left, and the fact that Gaussian processes, or the posteriors for Gaussian processes, have provable consistency, then it implies that the star term will tend to 0 as the number of data points tends to infinity. And that's basically the code there. So in essence, you just, and it's not very well written because we could have written this a bit slicker, but in any case, the covariance function is just based on evaluations of our base covariance function, and then the operations on it where u is, of course, the score function. And then the mean estimate is basically as we wrote previously here. So extremely straightforward. And if we go back to the table and look at the various approaches for averaging, then the control functionals approach is valid when f is unknown but can be evaluated, is valid when pi is intractable, it provides an unbiased estimator, and it can improve upon the baseline 1 over root n rate of convergence. So this is a good result. And I suppose the proof is in the pudding. Does it work? Is it useful? Well, let's look at a couple of examples. So here's a very nice contrived example, a one-dimensional example, where the integrand is the sine of x, and the density is just a normal density, it's just a unit normal density, so 0 mean and variance 1. So everything is nice and smooth here, so we know it's going to work. Okay? No nasty jumps or high energy transitions. Nice smooth sinusoid. So if we look at the top left-hand plot, bar plot, what you see is the mean estimate plus the quantiles of error associated with the standard Monte Carlo, so just taking the arithmetic mean. What we see is that as the number of samples increases, then the variance decreases, and so we get the standard 1 over root n rate of convergence. So that's good. That's standard. The competing approach, Riemannian sums, well, you can see that it certainly improves upon the 1 over root n rate of convergence. But if we go to the bottom line, we see that the control functionals approach, based on Gaussian processes, look at the rate of convergence. So, at 10 data points, we beat, by an order of magnitude, what we would achieve using a standard Monte Carlo estimate with 100 samples. And then pretty much the variance is 0 by the time we've got up to 30 data points. Now, of course, this is a very simple example, and it shows you how this structure, taking into account the fact that sine x is nice and smooth, taking into account the fact that the normalized Gaussian, again, is nice and smooth and well behaved, and infinitely differentiable. Okay, so that's nice, and that's the sort of results that you see in papers in ICML and NIPS. But let's look at a real problem. So you can ask as many questions as you want.
In the simple sine pi x case, any illusion on only constant f hat?
Yeah, the f hat, we basically just used we used a base covariance function which was itself infinitely differentiable. No, it's not an identity. It's full. Any other questions? Yes. Well, it's tractable. The normalized form is not tractable, but the functional component of it is. Yeah. Okay. In Bayesian methods, there is a technique called Bayesian model selection. And what is that? Well, imagine that you have a number of models that are all plausible to describe your observations, your data, or physical phenomena. And we've got a whole set of them. And so each model is indexed by 1 to k. So we've got model M1 up to mk. And these are all statistical representations of data. And each of these models is going to have a different set of parameters associated with them, theta 1 to theta k. And these parameters, well, the number of them will vary, or may vary, between the models. And the question is, what we would like to do is, given our data y, we would like to obtain the probability distribution of each of the models. So we would want the probability of model M1 given the data, the probability of model 2 given the data, up to the probability of model K given the data. And with that probability distribution, then, well, we can do a whole load of things. We can average predictions based on the models. We could look at the support that certain models have given the data and perhaps choose a subset of those models that are best supported by the data, and so on. But before we can do that, before we can get this probability of mi given y, we need to obtain the probability of the data y conditioned on the model. And the challenge here, typically, is that we don't know the probability of the data given the model, because the probability of the data given the model is going to be the integral of the likelihood, so that's the probability of the data given the model and the model's parameters, weighted by the probability of the model's parameters, and we integrate that over the space of model parameters. And typically, this integral is very difficult to obtain. It's typically unavailable in closed form, and estimates of it based on Monte Carlo can be extremely inefficient, because if you sample thetas from the prior, it may well be that those thetas from the prior are nowhere near the thetas in theta space that would give the likelihood, this function here, a high value. So it becomes very difficult to get good estimates of this marginal likelihood. And there's a whole area of work on how do you estimate this thing. And so the obvious approach of taking samples from P of theta I given mi invariably work very badly. Now, there is an approach to obtaining an estimate of this marginal likelihood called thermodynamic integration. How many of you have heard of this? Okay, so you're going to learn something. So I'll take my time. So what's thermodynamic integration? Well, it's actually a path integral, which it's basically a simplification of Feinberg's. Not Feinberg. Who was the physicist? Feynman. Feynman's path integrals. And in statistics, it looks something like this. We obtain a tempered distribution, P of theta, given the data, and T, some temperature, that is going to take the values between 0 and 1. So we take the likelihood, probability of y given theta, and we raise it to the power of t. So t between 0 and 1. And then we weight it by the prior p of theta. So what you can see is that when t is equal to 0, then p of theta given y and t is just equal to the prior. And when t is equal to 1, then p of y given theta to the power of 1 times p of theta is just the posterior p of theta given y. And the values of t in between are basically defining a path of probability measures or probability distributions between the prior and the posterior. And by using Feynman's construction, I won't go into the details of how we obtain this, but the log of the marginal probability, the thing that we're interested in, p of y, is equal to the path integral between temperature t equals 0 and t equals 1 of the function, which is the expected value of the log of the likelihood, and the expectation is with respect to this tempered posterior here. So you can see that what we're doing is we're taking a path from the prior to the posterior, and at each point we compute the expected value of the log likelihood with respect to that tempered distribution. And we basically integrate over that path. And what that does is it then, it gives us a far better estimator of p of y than just simply sampling from either the prior or the posterior, because we're taking the full path between the prior and the posterior. So the way that we compute this integral is we just compute it numerically, and so the estimate of the log of p of y is just going to be the sum of, so we're basically going to take, so this is just the trapezium rule. So we've got the estimate of the expectation with respect to ti plus the expectation with respect to ti plus 1. We just take the average and then weight by the difference between those two temperatures. So in other words, we take the unit line 0 and 1, we split it up into discrete temperature jumps, and at each of those jumps we compute numerically this expectation, and then we just weight them and sum them together. So in other words, what we've got is an awful lot of averages, right? These things here. Right? We've got a lot of averages, right, that we need to compute. So what we're going to do is we're going to apply it to a problem. And we're going to see if taking a control functional approach to estimating all of these averages, all of these expectations, is going to improve things for us. So the simple example we've got is a differential equation, right, which describes this oscillator. So x, right, if we solve for x, then what we get is this sustained limit cycle, so this oscillation. And the parameter that we're interested in is theta. Okay, so theta, just a scalar value, it's unknown, and it basically tells us how much nonlinearity is there in the PDE, in the ODE. So we put a log normal prior distribution on theta, so that the log of theta is normally distributed with a mean of 0 and, well, not a mean, a location value of 0 and a spread of 0.25. And we then sample from all of these intermediate tempered posteriors. So we have to use Markov chain Monte Carlo. So we basically have a Markov chain Monte Carlo running for each one of the temperatures. We run each of these chains to convergence. We then draw samples from them and numerically compute these things here. So what we want to do is use control functionals to see if we can improve upon the estimate of log pi of y given this path integral, this thermodynamic integral here. So can we do it? Well, here's the results. So the standard approach to thermodynamic integration gives us results that look like this. So as the number of samples n for each one of the expectations increases, then we get a decrease. But if you look at the variance of the estimate, it's fairly low, even at 20 samples. So the thermodynamic integral actually works pretty well. There's some more work that we did, which we published in the Journal of the American Statistical Association, and that improves things somewhat. But if we just apply the control functions to the thermodynamic integration, then you can see the rate of convergence, is just dramatically improved. And this is hugely important. So control functionals, really do make a dramatic improvement. And the key thing here is that what we've in essence done is we have exploited information about f and information about pi and been able to improve upon the estimator. But furthermore, even if f and pi are intractable, we can still use control functionals, whereas we couldn't use quasi-Monte Carlo or the probabilistic numerics Bayesian approach. So this is all quite nice. Now, I gave you this lecture so that you could understand and get the sort of mechanics of what we're doing and what we can subsequently achieve. Now I've got 10 minutes left. I think, have I got 10 minutes left? Yeah. To go through another 20 slides. So I'm going to cover the more abstract presentation this afternoon. Now this afternoon is the second last lecture, and so what I might end up doing is putting you to sleep before Yevgeny's presentation. So hopefully he will bring you back to life before we finish off. But what I'm going to do this afternoon is now present the more formal definition of control functionals using Stein transformations or Stein operators. And I'm going to, okay, so we've just seen this. I'm going to then work through the more formal definitions using Stein's method and looking at how we construct the estimator, what the rates of convergence are, and define it on a manifold. Okay? And look at that, and look at some quite large scale applications. And then I believe that session is actually a tutorial, so I'll then give you some examples to work through, or you could have a break, depends. Right, with that I am finished, and hopefully we've got coffee. Coffee now, is it? Sorry? In 8 minutes. So we've got 8 minutes for some questions. Yes?
If you want to estimate the quantile of f, you expect the quantile of f of x is the distribution type. Can you adapt the
Yes. Yes, because the quantile is just another function itself. It's the g of f. So the answer is yes. It's just another layer. We can talk about, the mechanics are straightforward, but the theory, still holds.
How does the length scale, because you use also process expands, how does the length scale affect the reduction of variance or the addition variance?
So a very good question. The question is, if you're using a base covariance function, which itself will have a parameter like a length scale parameter or whatever, how does that affect the rate of convergence? And the answer is it does affect it, and potentially it can affect it quite dramatically, because in essence what you're doing is you're then changing the type of, or the class of functions that covariance function would allow, would basically define. So in other words, the smoothness of the stochastic processes. So there is another layer of either cross-validation or whatever that needs to be undertaken to achieve that. So that's the one question you should always ask. So in the next lecture on Gaussian processes, as soon as you ask a question, always ask, what does the length scale parameter, what's the impact? Because it's the one thing that we tend not to talk about, because it has quite deep implications about the function spaces that we're dealing with. And the theory and the methodology is really still quite immature as far as that is concerned. Vadim. So very good question. So the question was, in the examples that we've given, we know what the well, in some cases we knew what the truth was. So examining how convergence is running is fairly straightforward. But what happens when you don't know what the truth is? How do you assess the rate? How do you assess convergence of the estimate? And the quick answer is that there are a number of heuristics that are readily employed in obtaining an estimate of whether the Monte Carlo estimate has actually converged or not. Yes. Yeah, so that's a great question. So the question was when you, it's in here, isn't it? So the question was when you use the thermodynamic integral, why don't you include the temperature T as another random variable? And the point is that you could, because you could put a prior distribution on T, and then and then basically what you would have would be the expectation of theta and T given Y, and then this integral would now be an expectation with respect to T. And the answer is that yes, you can do that. And in fact, if you do what you suggest and put a prior on T, you can actually get what the optimal distribution for T would be in terms of minimizing the variance of that estimator. So yes, that is something that you can do, and in fact, it's something that we've published. What the question is, what is the optimal distribution for the temperatures on the unit line for the path? And yeah, it turns out that it's actually a geodesic. It's quite cool. But anyway, that's another.
How do you choose the split dynamic practice? So you have to choose a training set, so to say, for the estimate of the control variable.
Yeah.
And another one, you take another set of the data.
Yeah.
So how should we split to have two variants?
Yes. So in the next lecture, I'll actually talk about what that optimal split should be. So there is an optimality result as far as, and it's actually fairly trivial, but yeah. Okay, 1 minute till coffee. What about one more question? Hey.
You mentioned the probability to get to the state. What kind of criteria are you looking at?
So in that case, it would be the, let me just remind myself. Let's discuss that over coffee, just exactly what it is, because I need to just think about it. I need a coffee to remember exactly what the criterion is. Okay, so you're all converts to probabilistic numerics. You've hopefully learnt a little bit about why functional analysis is important, why measure theory is important, why probability theory is important, and really cool. So we have a tutorial this afternoon. What I'm going to do, if you're happy, is that I will just continue with these slides and give you some of the more formal and more abstract general treatment, and then we can have a Q&A session. Okay? We're done.